Hi.
Hey,
Hey.
how's it going?
Okay, I guess I will start because it's at
Listen,
3.
seems like it's fine. Yeah, I guess it's just a connection. I'll share the link with everyone.
Okay, wait. I think. Okay, it's good to see that there's some people that can already hear me. Um, my stream is a bit ahead of your stream, so you're probably picking up what I said like 10 seconds ago, which is weird because then I don't actually know what you're listening to at that exact time, but I hope it goes well. If not, keep spamming the chat, and Lilia is going to be there to check, and she's gonna inform me on Discord. So I hope it's all good. Um, so I guess I will just start. Um, well, my name is Ella. Some of you might know me because I was your linear algebra TA in some of the work groups. And honestly, having linear algebra as a crash course is quite tricky because, well, there's so much basic understanding or like, I don't know, things you should know that underlie like every certain equation and proofs that might make it, I don't know, a bit more, how do I say this? Like a bit more clear, I would say. Like, because sometimes you find equations and you're like, yeah, well, why does it work? And I figured if it's a crash course, you're probably not that interested in that. So what I decided I would do is more or less go through every week, give you the key points that you need to pass the exam. And if you're interested or you're in doubt of some things, then I guess it's best if you just ask in the live chat. Then that way I know that I'm discussing things you actually want to know and not just getting you confused in things you don't need to know. Um, yeah, right now I don't see the chat, so I really hope Lilia will be informing me if there's anything important. But I guess we could start. So in week 1, there are very okay. Wait, I'm also getting used to this thing. Okay, yeah. So in week 1, oh, um, there's things you need to know. There's basically you have a system of, oh boy, this is really bad. Okay, you have a system of linear equations. And those equations, you need to put them in a matrix. And basically these matrices can be in terms of a coefficient matrix or an augmented matrix. And I think it's important that you actually know the difference. So the difference is basically that in coefficient matrix, you don't include whatever is after the equal. So for example, let me get out an example to actually show you the difference. Oh boy, I have to sign in. Okay, hold on. Okay. Let's say, for example, you have the following systems of equations. And I will really need to get used to this because it's awful. And I really apologize for my handwriting right now, but it's what I can work with. Okay, so basically, if you were working with coefficient matrix, then you ignore everything that happens after the equal. So you're going to put it into here, all the x variables, all the y, and all the z. So that will be 1, -1, and 1 for the first equation, and then a -3, a 4, and a -1 for the second, and a 1, -3, -2 for the third. And if you were working with augmented, that is basically including everything after the equal. So that will be essentially what you had with the coefficient. But then a bar, a straight bar, but yeah, cannot do that, obviously. And basically you want to include a bar, and then everything that this system of equation equals to, you want to put it behind the bar. Other than that, in this week, you basically, why this is important, I think, is more clear in the next week, but it doesn't really, I think it's pretty much clear. But other than that, in week 1, you also had to know how to basically have a matrix in echelon form, but you also needed to know how to have a matrix in reduced echelon form. And believe it or not, there's actually a difference between them. And I noticed during the workgroups, not a lot of people, also during grading, not a lot of people actually know the difference between them. And the whole thing with echelon form is basically when you have a matrix, I'll just fill in random numbers. You want it in a way such that you have, let's say, again, this is just random, so it might not actually be the reduced form, but you want it in such a way that you actually have what is so-called a pivot, and everything behind that pivot is just 0. And in this case, well, you have 3 pivots because you have the 1, the 2, and the 3, so that's 3 pivots. And the reason they're pivots is because everything before it is 0. And this is what you call an echelon form. And it's not necessary that you have always one more 0 in every next row. So you could have something like this, where here you have no zeros and here you have 2 zeros. That's still echelon form. You can also have something like this, that is also still echelon form. The key concept here is that always the number of zeros in a row, so here the number of zeros here in the second row should always be less than the number of zeros in the previous row. So for example, if I had something like 1, 2, 3, 0, 0, 1, and let's say 0, 1, 0, this is not reduced, this is not echelon form, because in the second row you have 2 zeros, but then in the third row you have a 1, 0, and that is, well, before the pivot I'm talking. So one way to make this into echelon form would be to swap row 2 with row 3, and once you do that, that will actually give you an echelon form. And now the difference between that and, well, the reduced echelon form would be that, oh boy, okay, that was a really bad deletion. The main difference between echelon form and reduced echelon form is now in echelon form, actually, what you need to have is, well, obviously what you need to have in echelon form, so again, zeros and pivots, but now the pivots should be equal to 1. And for every pivot in its column, it should be the only non-zero element. So meaning, in this example, this one is not reduced because, well, you have this pivot is not equal to 1 and this pivot is not equal to 1. But also in this column, the pivot is not the only non-zero element. You have this 2, and this 2 should have been 0. So normally, in an exam, if he asks you for an echelon form, you're always on the safe side to just give him a reduced echelon form. But then there's a difference between echelon form and reduced echelon form. And I noticed he actually asked something about it in Zuezo, where he asked for a reduced echelon form, but people still gave something like this. And I normally like to use it as a way to indicate at what point should I stop further reducing my matrix. And speaking of that, I think it's a perfect opportunity to maybe try an example to reduce. Because I noticed a lot of people had problems with that, where they were like, well, how can I start with this? And well, there's really no specific way of doing it. Okay, so I just got a question from Lilia from the live chat that a reduced matrix is always the identity matrix, and that is not true. That is a big misconception, actually. So for example, you could have something like this. Let's say you have a number here, a 2 and a 3, a 0, 1. Actually, no, I'll just... oh god. Okay, wait. So right now, let's say you have... actually, this can also go. Okay, wait, hold on. I'm coming up with a live example on the spot. So let's say you have a 0 here and a 0 here. So here, this can actually be a 2. Okay. So no, it's not always necessarily the identity matrix. This is in reduced echelon form, but this is not an identity matrix because you have the 2. And the reason why this is reduced is because this is my first pivot, this is my second pivot. They're both equal to 1, so our first check holds that their pivots equal to 1. And now in this column of the first pivot, it's the only non-zero element. And in my second column of the second pivot, well, the third column of my second pivot, why is this not working? There you go. It is also the only non-zero element. So our second condition that the column of pivot is the only non-zero element also holds. Therefore, this is reduced, but not identity matrix. The opposite is true though. So every identity matrix is reduced, but the other way around is not true. I hope that answers it. But going back on how to actually reduce a matrix, I would rather do that through an example. So again, there is no specific way of doing it, but I can give you some tips on what I would personally prefer to do. It's not at the minus here. Okay. I should maybe start writing a bit smaller because this is not fun. Okay, so what does it mean to reduce a matrix into its echelon form is basically we want to take this matrix and have it in some form where you have zeros and a pivot. This could be a way to transform it. It really depends on the dependencies and everything. But basically, what you want to do, or what I like to do first, why is this acting up? Okay, yeah. What I would rather do first is try as much as I can to make whatever is at the beginning of a matrix 0. So for example, in this example, you could take the third row, subtract it from the first row, and there is our first 0. So that's 0, minus 3, minus 1, minus 2, and then minus 3. Yes, okay. Just double checking my basic maths here. And then again, I would try to create another 0. So I would, well, I can see that this one can also become a 0. So I will say, okay, then I'll take the second one and I'm going to add it to 3 times the first one. And this will give me minus 3 plus 3, so that's 0. 4 minus 3, that's 1. And then, well, a 2 here. A 0 minus 2 minus 3. And then I see that I already formed my first pivot here. So I will try to form another pivot here, because this is also my second pivot. So it seems like it's best to turn this to a 0 now. So the way to do it is, well, you could either now, to make this specific number a 0, you could either now add it to the second row or 2 times the first row. But if, let's say, you picked the first row, so you'll say that R3 will be minus 2 times R1, you will notice that in this 0 that you already transformed, now you'll get 0 minus 2. You lost whatever value here. You lost the 0 here that gave you the pivot property. So that is definitely something you want to avoid. Once you set something to 0, you want to avoid adding it to another row that will change the 0 back for you, because then you're going back in cycles. So instead, it seems like a better option to go with row 2, because that 0 will not be affected by that 0. So instead, you're going to say will be plus 2 times R2. And that should give you 1 minus 1, 1, 0, 1, 0. Actually 2, my bad. And then 0, 0, 1. Just for the sake of space, I would like to... No, that's not what I wanted to do. Hello. Okay, apparently it won't let me, but basically we ended up with this. We ended up with this, so now I'm just going to just delete this and actually put it in again. Sorry, I'm with a Mac, and the softwares that actually like support such things are not that good. So, but we ended up with this. And this is still not reduced echelon form, because even though your pivots are equal to 1, this column right here, it still has another non-zero element other than the pivot. And same goes for the third column for this pivot. So you still need to do some more work. And at this point, it's easy to see what you need to do, because knowing that this is your pivot, you obviously want to make this 0, and you would want to make these two 0 as well. So now it's a bit more clear in what direction you should be going. And well, to do that, I would just say R2 will be R2 minus 2 times R3. So that will be and then I will say take R1 to be minus R3. This is one way of doing it. This is to show you that you could actually do multiple rows added together, but I would definitely not recommend this, because during an exam you will definitely get confused. So I would go for something simpler, where I would do it in 2 steps. So I would say R1 will first be R1 plus R2. That will give me something like so. And now I need to get rid of this one, so I'll say R1 again will be R1 minus R2. So that will be, and in this case, it happened to be the identity matrix, but it's not always the case. So that's one way of reducing stuff. And honestly, I think there's not much I can help you with this. It just comes with practice. So if you're still a bit unsure of how to do it, you just need practice. And just to remind you, the things that you could do is the following. You can basically swap rows. You can add rows to each other. You can even say something like row 1 will be row 1 plus a constant times row 2. So you can add rows, you can even multiply a certain row. But yeah, other than that, I think one of the biggest mistakes I've seen while grading was somebody saying something like, some people tried to basically do 2 operations at the same time. So they did something like R1 will be R2 plus R3, and at the same time R3 will be R1 plus R3, let's say. So, and if you do this at the same time, this is actually quite wrong, because R1 is dependent on the answer of R3, but at the same time you're changing R3. And that led to a lot of mistakes. And I've noticed it was actually a very common mistake people did. So one, make sure you're not changing a row while that is dependent on another row. So in this case, do not do this R3 even though you're changing R3. But I would say just don't. Just do it step by step. It's not going to save you any time. It will only confuse you. So just do it. Just separate them. But other than that, I think we should move on. Oh god, this is really, really bad. Okay. You're just going to hear me complain between my selection deletion process. But other than that, now we have a reduced echelon form. What use can we make out of this? Well, it's easier to find solutions through it. So if we go again back to augmented matrices, so let's say we had something, or like the identity matrix, let's start with that. That's really easy. Oh no, I forgot the bar. Let's say you have a matrix like this. Then what this is really saying is that if you took all the x values here, all the y and all the z here, you're going to get something like this. So x plus 0 times y plus 0 times z is 3. And 0x plus 1y plus 0z is 4. And 0x plus 0y plus 1z is 5. And this is much simpler to solve than what we initially had with all the other values, because here it's very clear then that x is 3, y is 4, and z is 5. So this is the easiest case you would get, the identity matrix. But then there's multiple ways to reduce an echelon form. You might get different, I don't know, results out of it. So you have a term called consistent and inconsistent. And basically what those two mean is that if you say that a matrix or a reduced echelon form is consistent, it means that there's actually a solution to it. And if it's inconsistent, then there is no solution to it. And yes, believe it or not, there are cases where you could get a system of linear equations such that you don't have a solution to. And that is the case when you get a matrix and you reduce it, an augmented matrix, and you reduce it and you get something like, let's say something like this. Let's say this is for x, y, and z. Then this is what it's really saying, is that you have x is 5, and then you have the second row says something like this, which basically says that 0 is 3. And even I know that this is not the case, that this is just weird. And in that case, you know that 0 cannot be equal to 3, which means this matrix is nothing but really just bullshit. There's no solution to it. And this is the case of inconsistency. So in the exam, if he asks you, I notice sometimes he asks something like, he puts a variable a here, and he says, well, what values for a would this matrix become inconsistent? And well, you have to find a such that the row here now is just all zeros, and whatever after the augmented bar is a non-zero element, like this 3. A big mistake I saw is that people sometimes had a matrix like this, and they said that this is inconsistent. And this is actually wrong. Just because there is a 0 here, this actually makes complete sense, because it says 0 is 0, which is the case. So this is consistent, actually, not inconsistent. So what you need to check for is that everything behind the bar is 0, but whatever is after the bar should be greater than 0. So this is consistent and inconsistent matrices. But then again, you could actually interpret stuff from that. So now, if you happen to have, well, if you have inconsistent matrix, well, then you know there is no solution. But if you have consistent matrix, you either have a unique solution, or you actually have, well, I'm not sure what they call it, but just basically solutions, where you actually have multiple solutions and not one unique solution. And the cases for these are, well, if you have a matrix, actually in a basically a more straightforward way, if the number of your pivots is the same as the number of your variables, then you know that you're going to have a unique solution. And here, if you have the number of pivots is less than the number of variables, then you're going to have multiple solutions. And what this actually means is, well, let's assume a matrix here that is just 0, 2, 0, 1, 0, 0, 0, 1, let's say. And actually, let's assume this is an augmented bar. Let's say this is 4, this is 3, this is 2. Well, 1, this is not reduced, but it's okay, I can work with this. Let's assume this is for x, y, and z. Then here you have 3 pivots, 3 variables. So from this you can actually expect that you have a unique solution. And that is, we can check. You have here x plus 2z is 4. You have y is 3 and z is 2. I interpret this from here. So basically I made an equation out of this and we come up with this. But here you know that z is 2. So here you know that x plus 2 times 2 is 4. Therefore x is 0. And no matter what kind of echelon you get, really, whatever operations you do, I will guarantee that you will get this same exact solution every time. And that's why it's unique. The only way you might not get unique solutions and multiple solutions is, well, if you actually have the number of pivots less than the number of variables. And what that actually means is, let's assume you have something like this. So let's say you have 1, 0, 3, 0, 0, 1 for simplicity, 4, 5, and let's assume this is for x, y, z. Here I only have 2 pivots. And again, this is not reduced because in this column you have a 3 and your pivot is not the only non-zero element, but I can still work with that. What this would translate to is you have an x plus 3z is 4 and the z is 5. And you don't know anything about y, really, which is a bad example. So let me change this actually. Let's assume this is 1. Because if y is 0 in the both cases, then you actually only have 2 variables. But let's assume this is y, so I'll just add y here. You don't actually have a specific value for y, meaning that you just need anything for y that would satisfy whatever you put here. If you know z is 5, then you can say now you have the equation y plus x plus 15 is 4, and z is just 5. Then really you can pick so many things such that this actually holds for different x and y values. So one example could be y plus x is 4 minus 15, which is minus 11. I'm actually not sure. What is 15 minus 4? Jeez, I should know this. Yeah, I think it's minus 11. But it really doesn't matter. The point still holds. You could still find whatever number is here. You could still find many cases where a combination of y and x will give you minus 11, like y is minus 6, x is minus 5, and you have z is 5. You already know that from here. You can also have something like, well, you have y is minus 9, x is minus 2, and z is 5. So you start seeing that, okay, this system of equations can have multiple solutions. And the reason is because you had the number of pivots less than the number of variables. So by now you could sort of connect that the number of pivots is dependent on what kind of solutions you get. The pivots actually represent your variables in some way, in some sense. And yeah, this is how you can know whether also a matrix is consistent or not. If it's consistent, sorry, if it has multiple solutions or not. You could just right away look at the number of pivots you have, the number of variables you have, and you can already guess, well, okay, this one will have a unique solution or not. And one of the exam questions I think you might get is, okay, you have this system of linear equations, can you have a unique solution for this? And what you need to do then to first reduce it to echelon. So it's important that you first reduce it to echelon, otherwise you don't actually know how many pivots you actually have. And then from after that, you count the number of pivots and compare it to the number of variables. Another question you might get is he might substitute one of the values with a. So for example, you can have something like 0, 3a, 0, 0, 1, 4, 5, 6. And he will ask you to find values for a such that this matrix will give you a unique solution. And the way to do it is, again, reduce it to echelon form and make sure that this, well, just basically make sure that the number of pivots are going to remain equal to the number of variables. And I think you'll find a lot of questions regarding that in the assignment. I think if we have enough time at the end, I can go through some, but the general, as long as you know the general idea, then I think you should be fine. Otherwise, you can tell me in the chat and we can go through some. But then now there's also more things to interpret out of this. Now, if you do happen to have a solution, so let's say you have a consistent matrix, this can either be, again, unique or not unique, so multiple solutions. If it happens to be unique, then let's say you had something, I'll just give you a value, 3x minus 2y plus z will give you another value. Then if you put these into a matrix and you solve it, and it happened to be that you can get a unique solution out of it, actually you will need one more if that is the case. Then you can safely assume that there is an intersection between them. Because what this really does is, between different lines, okay, I will really have to get this correctly. Okay, that's really bad, but whatever. But within different lines, you're gonna have an intersection point. And what the matrix is doing is that you're trying to solve these set of equations such that you get one exact x value, one exact y value, and one exact z value that happens to be the case in every equation. And what that really means is just an intersection, really. So if you have a unique solution, you know you can have an intersection. And if you have multiple solutions, then you know that you can have a coincide. And what this means is that, well, you have a line and you have another line that is just over it. So that basically they're on top of each other. And, well, it would make sense because that means that you have multiple points here that fit both equations, right? And if you have inconsistency, aka no solutions, that means that the lines are actually parallel, because then you cannot find any point that is actually can satisfy both equations at the same time. And that was pretty much week one. So questions he can ask is, well, reduce a matrix, either in an augmented way or a coefficient way, they both hold. It's the same procedure. He can ask you whether a matrix is consistent or not, and that is basically you need to find out whether there is a solution or not, and an easy check is to reduce it. So first reduce it, and then second check if you have an entire row that is 0 and then gives you here an element x such that x is greater than 0, then you know this will give you no solution and hence it's inconsistent. And then he can also ask you to provide a unique solution. He can also ask you whether two equations intersect or not, and to solve that, well, you need to check whether you can find a unique solution or not. He can also ask you whether they're parallel or not, and that means that you will not find a solution to it. But yeah, I really think it's important overall through the entire course. Actually, I think the only reason I passed this course was because I only did the assignments. So if you go through the assignments, I will guarantee you that you will, I bet you that you'll actually pass. And that's really what you need to do. But I think that's enough about week 1, unless you're gonna ask me questions about it, then I can continue a bit longer. But for now, let's start with week 2 until I do get a question. In week 2, you're basically going to discuss homogeneous and non-homogeneous systems of linear equation. We're also going to discuss basic and particular solutions. We're also going to discuss generic equation. Okay. I think I would like to personally open something. Just give me a second. So basically, there's a lot of underlying material here, but what I think you should just know is a homogeneous linear system of equations is basically if you have a matrix and whatever values you have here, everything after the bar is just 0. That means that all the equations just result in 0. Non-homogeneous, on the other hand, could really just be whatever you want. So you can have x, y, z here, whatever value you get, but then x, y, and z is not equal to 0. And well, basically, for a homogeneous linear system, so if you happen to have such a matrix, this can give you what is so-called the basic solutions. And those basic solutions are not going to be equal to 0. So in other words, let's select all and then delete. You have a vector. So you're going to have vector 1, which is, let's say, 2, 3. Vector 2 is 1, 3. You have a third vector, let's say 5, 2. You want to find coefficients of those. So you want to find a1 times v1 plus a2 times v2 plus a3 times v3, such that this is always 0. So if you put it in a matrix, you'll get something like 2, 3, 1, 3, 5, 2, 0, 0. And what you're really looking for is a1, a2, a3, where this is the case. And whatever values you get for a1, a2, or a3, and a3, those are your basic solutions. how do you get those? Well, there's actually a procedure for it. First, I'll just tell you how can you get such things, and then I'll explain what they actually mean. So let me bring out an example. Oh god, that is a big example. Okay, let's say you have the following matrix 2, 3, 1, 2, 1. Let's say you have the following matrix and you want to find, well, the basic solutions. What you need to do is step 1, I would say mark your pivots. So this is a pivot, this is a pivot, and this is a pivot. Again, these are pivots because everything behind it is just zeros. And this is also in echelon form because you have pivots and whatever behind it is 0, and the number of zeros in this row is less than this row, and etc. So first step is mark your pivots. Second step would be you want to, for every non-pivot, so this one, for every column without a pivot, so this column has no pivots, and this column also has no pivot, you want to one by one just remove such a column and then reduce it to echelon form, find a solution. In this case, column number 2 is removed, and you need to keep track of that. I'll tell you later why. So now you're gonna get something like 2, 0, 0, 1, 4, 0, 2, 1, 0, 1, 1, 2, and then 1, 2, 6. What you need now to do is basically reduce. So column 2 is removed. I would say here reduce to echelon and find, well, here reduced echelon, that is, and find solutions. So let's actually, I would say let's actually try to so let's actually try to solve this together, I would say. In this case, well, okay, this one, this pivot I can turn into 1, so I'm going to take row 3 and I'm going to divide it by 2. So now you're going to get 2, 1, 2, 1, 1, 0, 4, 1, 1, 2, 0, 0, 0, 1, 3. Then I can also now maybe change this one to 0, and well, I can also change this one to 0. This will be useful anyway because you know that this pivot should not contain anything else other than that pivot that is non-zero. So I'm going to say R1 will be R1 minus R3, and R2 will be R2 minus R3. So that will be 2, 1, 2, 0, and 1 minus 3. Oh, actually, sorry. A very good point to make is that, again, this is actually okay, so this is actually a common mistake that people do as well, and I also fell for it. When you're trying to find basis solution, again, we're trying to find something such that everything after the augmented bar is 0. Meaning, right now, you're not actually finding the basis solution, you're just finding the solution of the systematic equations because you're, well, solving them. But what we're actually trying to do now is find the basic solutions, another vector, such that if you multiply it to those vectors, you're going to get zeros here. So actually, this is not entirely correct. And I missed a very important first step. I'm going to delete this as well. So actually, your first step is, well, get rid of whatever is behind the bar, because now you want to write it in a way where, again, the a1 v1 plus an vn equals 0. So this will basically, in other words, translate it into this augmented matrix. And this is equivalent to if you didn't really include whatever is behind the bar. And I got a lot of questions before on why is that the case, and well, it's simple. If you're going to apply whatever transformations you're applying, so let's say R1 will be R1 plus R2 just for fun, whatever you do here, whatever is behind the bar will always remain 0, because if you multiply it, it will remain 0. If you add it, it will remain 0. So in other words, you're wasting ink. So what you could do is just completely ignore that. So first thing is, well, get rid of whatever is behind the bar, which means make your augmented into, well, a coefficient matrix. This will give you 2, 3, 1, 2, 1, 0, 0, 4, 1, 1, 0, 0, 0, 0, 2. And then you mark your pivots. Then you start getting rid of columns that do not actually have pivots. And in this case, again, I will start with column 2. So I removed column 2. So now you'll get something like I cannot even read. Jeez. 1, 1, 2. Because we got rid of the second column. And now you would want to solve this. So again, I am going to divide row 3 by 2, because then I can actually get a pivot there. A reduced pivot, that is. What I can also do is I can get rid of this.
When you have time, can you please explain what homogeneous and non-homogeneous mean?
Okay, I got a question of what are homogeneous and non-homogeneous actually mean. Oh boy. I would rather discuss this at the end, so hit me up, or whoever asked the question, you can Discord me, because it's really in details, and I don't think it's that important for you to know. But it's, again, essentially what it means is you basically want... I will actually explain to you at the end what it actually means. Just give me some time here. But basically, you're going to reduce this to echelon form, and let's just skip to the fun part. You're gonna end up with something like, I think after you reduce it, you're gonna end up with something like this. And here comes the second most common question is, okay, well, what do I do now? Because you cannot really further improve on this. And well, my answer to that is, well, let me actually free up more space here. I'm just gonna get rid of all of this, honestly. So right now you got at the end, okay, actually, let's clean the entire thing. The following example, we reduced it, you end up with something like 2 minus 7, 0, 0, 0, 4, 1, 0, 0, 0, 0, 1. I personally don't like to do, as much as I can, I'd like to avoid creating fractions in my matrix. So I would personally stop here, but you can further divide by 2 and divide by 4, row 1, row 2 respectively, to get like the pivots 1. But I personally find that, well, I don't like to do that. So what do you do now? Well, basically find the solutions. From this, you can deduce, remember those are our a's that we're trying to find. And basically what you're doing now is you're getting something like this. 4a2 plus a3 is, because remember we had an augmented bar here and everything behind it was 0. And well, okay, now the question comes, how many solutions can I get out of this? Well, I don't know if you noticed or not, but the number of pivots that you have are actually less than the number of variables, meaning you're going to have a lot of solutions, just many, multiple. So what you need to do now is basically make up your mind. From here, from the first one, you can know that you have 2a1 is 7a2. So let's say you can pick something like, okay, I will do a2 to be, a2 will just be, actually let's do a1 will be 7 over 2 a2. Yeah. And then we also have from the second one, a3 is just minus 4 a2. And then from the third one is a4 is 0. So now you actually need to construct your vector where you need to put here a1, a2, a3, a4, and a5, because originally you had actually 5 variables, and we removed one non-pivot column. And if you actually recall, we removed the second column. And this is where it's important to keep track of which column you remove first. We removed the second column, so by default, we know that this second column, God, why is this not working out? This second column, oh boy, is going to be 0. And a1 is 7 over 2 a2, so just pick something. I will put, oh wait, okay, I'm probably confusing you here, but this is actually a3, a4, and a5 because we removed column a2. See, it's important to always keep track of which column you're removing. So actually here is 0. I will just pick, I'm just gonna pick, I'll pick a3 to be 1. So I'm just gonna put 1 here. That means that a1 now is 7 over 2. And now this a3 is 1. So now you have 1 is...
Someone's asking if you can find the solutions like this from the echelon form, or if you actually have to put it into reduced echelon form.
Okay, so I just got a question that, well, can I find the solutions from this echelon form, or do I have to put it in reduced echelon form? And well, I would say it really depends on your preferences. I don't think you have to, unless it's actually specified in the question that you have to use reduced echelon form. But when it comes to basic solutions, I normally don't finish all the way to the reduced echelon form because, like in this one example, I will actually start getting fractions and I find them a bit messy. So I just stop here, and that is when I find my pivots. But it's really up to you when it's about finding your basic solutions, because at the end you're going to end up with the same kind of format whether you reduce it or not. It's just a matter of, well, picking your answers. So back to this big mess. Let me just, honestly, I feel like I'm just confusing you here, which is quite understandable. So let me just do this real quick again. Okay, but now I promise you I'll try to be cleaner. Okay, so right now you're gonna have you wanna find your A1, your A2, your A3, your A4, and your A5. You already know A2 will be 0 because that's the column you removed. So now let's try to find other stuff. Here from this equation, you know that you have 2A1 minus 7A3 should be equal to 0. From this one, you can deduce that A1 will be 7 over 2A3. So this is your first equation. From it, well then, if I had to find A1, I'm just going to say A3 will be equal to 1, because then you could, well, actually 2. Let's put it 2, because then you can get rid of the stupid fraction and you'll get A1. From it, you can deduce that A1 will be 7. So right now I found A3 and I found A1. And I found them because I decided they will be, that's the case. As long as you maintain the relations, you should be fine. So now we have to find, well, A4 and A5. A5 is already on its own. So you have a second equation you can find is that A5 is equal to 0 because it's the only one here that is actually set to 1. So you know, okay, A5 is 0. Nice. So now we just need to find A4. And A4, well, you can know it from this equation because in the first row it's set to 0, and the second row it's set to 0, so you don't actually get A4 out of it. So the equation from the second row you deduce is that you have 4A3 plus A4 is equal to 0. So you know that A4 is just minus 4A3. And we already said A3 is 2, so that will be minus 4 times 2, which will be minus 8. So you'll have here A5 will be minus 8. Okay. Now that's the first basic solution that you found is 7, 0, 2, I cannot type, minus 8, 0. That's the first basic solution. I'm actually going to write that down somewhere else so that I can go back to it. So 7, 0, 2, minus 8, 0. And now, whatever, I get a question, but what if I pick another number? What if I picked A3 to be 1? Well, let's do that. I will pick A3 to be 1 now. So I'm just going to get rid of this for more space, this part, and this part. Okay, what if I decided A3 is going to be 1? Okay, well then, you know that your Okay. Then you know that your A2 is still 0 because that's the column you removed. Your A3, you said I decided A3 will be 1. Sure, you do you. A1 now will be 7 over 2 because you decided A3 is 1. You still have A5 equals 0 because that was not dependent on anything really. And now you're left with your A4 again, which was 4 times A3 plus A4 is 0, so A4 is minus 4 A3. And you decided A3 is 1, so you know that A4 is minus 4 times 1, which is minus 4. So what you end up with is, well, 7 over 2, 0, 1. Where is my 4? Oh, there. Minus 4 and 0. And now if you had to compare these two, you'll notice that one is just a multiple of the other, really. And it's actually true. So that's how you can check. That's why it doesn't really matter what kind of, well, value you pick for your A's to be. Because, well, after all, they're going to end up to become a linear relationship of each other. And this is basically what basic solutions or basic vectors are. If you have a vector space, what it's saying is that you want to find independent vectors such that every other vector in this vector space can be represented using those vectors. Just like in this case, whatever vector, it's proven that whatever vector you're going to find, it can be formulated from its basic vectors. So you can perform some certain multiplications and additions to the basis vectors such that you actually get the vectors you want in that vector space. And so what they actually try to do to find the basis solution is that they try to find independent vectors, and that's why you set everything after it to 0, because you're trying to find sort of what we call a homogeneous solution. And from it, they say that any non-homogeneous, so any non-homogeneous vector could be derived from a homogeneous vector or a homogeneous solution. So we're still not actually done. We still have to now remove another, we had 2 non-pivots, so this is only one basic solution. So I'm going to select all and delete. And I'm gonna go now to find the next basic solution. So that is when we had to remove the 4th column. So just if you were not actually putting this down and you were not like following up, just trust me that now originally we had a matrix, and trust that I removed the 4th column. So this is actually A1, A2, A3, and this is A5, because I removed the A4 because it was non-pivot. Now if you reduce this to echelon form to make your life easier, you can do that. What I will just do is, well, I'm going to take R2, divide that by 4. So now I'll get something like this. And, oh, interesting. Yeah. Also, I will get rid of this because, well, I can do that and it will make my life easier as well. So I'm also going to do that. When you're reducing, all you need to think about is how can I make my life easier? And, well, that will put you on the right track. So complicated, multiple transformations that you're doing on a single matrix, big no-go. Fractions, try to reduce that as much as you can. Like, try to make your life easier. But basically, you end up with this. You can't really go further. You could if you want to. I don't want to because I will have fractions. So I'm just going to stay here. And I'm going to now find my basic solutions by just picking. So again, now I am going to have 2a1 plus 3a2 will be 0. The reason I'm saying this is because you're trying to find those. From this, you can see that a1 is minus 3 over 2, a2. So that's one equation you're going to use to find it. Again, we're trying to find a1, a2, a3, a4, and a5. Yeah, you already know we removed 4, so this will be 0 by default. And again, you're just going to pick whatever you want. So I'm going to say a2 will be 1. So I'll put this as 1. So you know from this a1 is minus 3 over 2, and you sort of just move on with that to find a3 and a5. And just for the sake of time, trust me on the following. You're going to end up with now 2 basic solutions. One because you removed the second column, and the second one because you removed the fourth column. And again, the reason why you're removing columns is because they were non-pivot columns, meaning that column did not contain any pivot. Keep that in mind for a bit. But basically, you're going to end up with the first solution to be, just trust me on that, and it's still a multiple, so we've seen it in multiple forms. And now your second solution will be which is great, you found your basic solutions. And actually, there could be a question of how many basic solutions can you get out of this matrix? And the answer to that is that the number of basic solutions is just going to be the number of non-pivot columns, because for every non-pivot column, you reduce the matrix and you find solutions to it, right? This means basically the number of variables minus the number of pivots. This is equivalent. And now the next part of this is to find what is so-called a particular solution. And what this particular solution means is that what you need to do is just, again, ignore everything behind the bar. So put everything behind the bar to 0. 2, you're going to remove now all non-pivot columns. And then you're just going to find unique solution. In our previous, like the example I was working with, that means you're going to remove both the second and the fourth column. By the way, these examples are from the assignment, so you can look at them again. But what you're going to get is, oh, actually, my bad. When you're finding the particular solution, you actually want to find a unique solution. And I'll explain to you what this actually means. But in this case, you don't actually get the well, the coefficient matrix. You want to keep whatever is behind the bar, because otherwise you cannot actually find a solution to it. So you'll get 1, 1, 0, 4, 1, and a 0, 0, 2, and here you have a 1, 2, 6. You're going to simply just solve that, just how like we did in week 1, and you will get an answer like the vectors will be, again, you removed the second column and the fourth column, so you know that those are equal to 0, and whatever values you find for the first A, the second A, and the third A, you'll put here. And now you're gonna end up with, well, what we call a generic equation. And what that means is that any coordinate can be made using the particular solution you found plus all the basic solutions you found. And I will explain to you in a minute what that actually means. So in our case, what we started with, you're going to have the answer, or the generic equation, will be this plus a scalar multiplication to your first basic solution. So that was your 7 over 2, your 0, your 1, your minus 4, 0, plus C2 times your second basic solution, that was the minus 3, 2, 0, 0, 0. And actually what's really going on here is you're trying to find a way to represent a certain coordinate, so again, a coordinate in a vector space. Meaning, I don't think he'll actually ask you theoretical work, but I think it's important for you to understand what's going on. So what is actually going on is the following. You have, let's say, a three-dimensional space. So let me actually pick a not that bad of an example. Oh god. Okay, let's say you have a three-dimension. So you have a z, an x, and a y. And because you have so many ways to represent this vector because of your basis vector, what is actually going on is that you want to represent a certain coordinate. So let's say in this space, I want to represent a certain coordinate. And because there's so many ways you can navigate in that vector space to that coordinate, what you're saying is, okay, I will go to a particular solution that is my unique solution. That was the P that you found. Let's say this particular solution is at, well, 1, 0, 0. And I want to go to a point coordinate Q, let's say of, well, actually Q would probably be somewhere here, of Q, let's say 0, 1, 0. And what the basic solutions are telling you is actually the direction on how to get there. So you want to find, well, in this case, 3 vectors or 2, or well, 3 points or 2 points or 3 directions to actually help you navigate. So I'm just going to say you want to find a vector u and, well, a vector v such that it will help direct you to the coordinates you actually want to reach. And the way they do it is that it's easier if you start from the origin, go to a particular solution, and that is the unique solution that you find. And from there, start defining your basic solutions, so your vectors of, okay, what direction should I go? So again, if I had to put the generic equation, it was the particular solution plus your basic vectors. And this basic vectors is actually a constant times your first vector.
There's a question. Luke stated in one of the lectures that there are an arbitrary amount of particular solutions. Can you elaborate on that?
Okay, I just got a question that Luke said there are arbitrary amount of particular solutions. I guess that could be the case, but the way to find them is, well, find a unique solution. And that is one particular solution that you can be very confident about. I do think, yes, you can find many particular solutions in like, well, your vector space. But a way to find one coordinate that is actually a particular solution is, well, to find a unique solution. So finding a unique solution doesn't mean it's the only coordinate that will happen to be particular, but it's definitely a coordinate that will be particular. But then back to this, basically here what you were trying to find is this is some constant times a vector, and these two vectors will basically tell you or guide you in which direction to go from the particular solution. And these constants actually tell you how far to go, as in, well, between quotations, distance, like distance. So this U represents here a U and a V. So first you go to the particular solution, and from it you want to navigate, well, in this basic solution direction 1, basic solution direction 2, and whatever constant you're actually multiplying to tells you how far in that direction should you go to actually reach a certain point. So this is actually why you need generic solutions and why you need bases and basics, and the whole theory behind homogeneous and non-homogeneous is what helps you prove that this actually works. So I don't really think it's smart to go in depth on that because I think it will only confuse you for the exam, but I would recommend going through the assignments again and just working your way through it. But from it, one important things you can, well, I think that's all he talked about in week 2. Just a small recap, because I think I kind of confused you here and there. 1 is the number of basic solutions is the number of non-pivot columns. And actually, this is a name I made up. There's actually no such name. The formal way to do it is the number of variables minus the number of pivots. That is actually, well, formally makes more sense. The second point to make is, well, okay, how can I find my basic solutions? Well, first you want to mark your pivots, then remove, I'll put a step 0 because, well, we're programmers. You want to first do it into a coefficient matrix, because again, everything behind the bar will be 0 anyway, so might as well save some ink. You're going to mark your pivots, remove all non-pivot column. Well, actually, all is a bit misinterpreting. You remove non-pivot columns 1 by 1, and for each find your basic solution. So that is, well, you remove the non-pivot, find a solution, remove the second pivot you find, and during that, if you remove a certain column x, then the a at this x will be 0. So whatever you fill in, if you remove that column, you're going to place a 0 there. That is the answer for that specific column. So at the end, your basic solution should have as many variables as you actually initially had, even though you've been removing some columns. Do not forget that. And yeah, other than that, how do you find your particular solution is pretty much here, use the augmented matrix. You're going to remove all non-pivot columns, and then just find a unique solution. And that will be your particular solution. And again, whatever vector you get, it has to have the same number of variables you initially had, even though you removed columns. And then your generic equation will be just your, well, particular plus your constant times your first basic solution, and the constant times your second basic solution, up until I don't know how many basic solutions you found. So whatever basic solution you found. And that was pretty much week 2. I will not get into details on, well, proofs and theory behind it much. I would rather move to week 3, but you can always ask me questions if you're interested. No. Okay, so let's just move into week 3. I see I'm using too much time and we're still not halfway through. Okay, I will quickly go through that one because there's not a lot of things you need to know, but you need to know how to find independent, whether a matrix is independent or a set of vectors is independent or dependent. And well, they're independent if you happen to have, actually, they're dependent if you happen to have, I would say, the number of pivots, again, less than the number of variables. And the way you can think about it is, I don't know if you remember or not, but when we had that case, when we had multiple solution cases, we usually ended up with something like x plus x2 is something like 5, let's say. And you see that one value of a vector actually depends on another value as well. So you can see there's sort of a dependence relationship here. As in when we had independent, we always had something, x1 is equal to something, x2 is equal to something else, nothing dependent on x1. So one way to find whether something is independent or dependent, well, again, reduce to echelon form. So go to echelon form and just check the pivots, I would say, really. I would say it's more than enough, but I don't know what kind of questions you will get. Maybe you'll have to solve them. But this is the way I did it, and I passed. So, then he also discussed multiplication, transpose, and identities. Okay, a lot of people actually struggle with the multiplication, so I will go through that one. Okay. So let's say you have the following multiplication that you need to do. Let's say you have here A is 1, 2, 3, 4, 5, 6. B is 9, 8, 6, 5, 3, 2. First step is write their dimensions. Here you always do rows by column. So in this case, you have 2 rows by 3 columns, and in this case, you have 3 rows by 2 columns. Then you ask the question of, okay, can I multiply them or not? And how do you know if that is the case? Well, it is the case if the column of your first matrix is equal to the row of your second matrix. And that is very important, because otherwise you'll be wasting your time in trying to multiply something that cannot be multiplied. Visually, how to check that this value is equal to this value. If it's the case, then you know, actually, you're going to end up with a 2 by 2 matrix. The way I do it is I just completely ignore these. You'll have a 2 by 2 matrix in this case. So if I had something like 4 by 5 and 5 by 6, what is the matrix I will end up with? Well, 4 by 6. This actually makes sense when you multiply. So let's actually just multiply them real quick. So this was a 2 here, this was a 3. So what I like to do is I like to place them as so. And what you will need to do is we said we're going to get a 2 by 2. We already showed that. I showed you that. So we had a 2 by 3 and a 3 by 2. That will give you a 2 by 2. So you know that you need to be expecting something like this. And what you're actually doing is you're taking every row with every column. So in this case, what you need to do is you're going to multiply 1 by 9, add it to 2 times 6, add it to 3 times 3. And this will give you this value here. So let me write that down so it's actually clear. So what you'll do is 1 times 9 plus 2 times 6 plus 3 times 3, and this will give you a value I will not waste time showing you how bad I am at basic math, so let's just move on. Then for this value, you're going to take the same row multiplied by this column here. This will give you this value. So what you do for this one is 1 times 8 plus 2 times 5 plus 3 times 2, and that will give you a second value, and that will be a 2. And then, well, you don't have any more columns, so you're going to move on from this row. Let's pick a different color. So now you're going to go to the second row, and you're going to multiply this row with every column you have in the other matrix. So in this case, this row will go with this one. I can see it's getting really colorful in here. So 4 by 9 plus 5 by 6 plus 6 by 3, that will give you something. We'll put that something here. And finally, you have one more column to go, so you're going to take this same row again. You're going to multiply it by this column to get this value here. So that will be 4 by 8 plus 5 times 5 plus 6 times 2, and that will give you a 4, and that is your value here. So again, first thing, check if it can be multiplied, and that means that the row of your first matrix is the same as the column, the numbers of your second matrix. And then 2, if that's the case, then just multiply them as so. So that will be, you'll multiply every row with every column. And once there's no more columns, you go to the second row, that same row multiplied with every column. And that is the multiplication. Now we're gonna go to transpose. I'm gonna select all, delete. What does it mean to transpose something? Well, basically what it means is you just want whatever was in the row to become whatever was in the column. Meaning, let's try to transpose what we originally had as a B. So B 9, 8, 6, 5, 3, 2. What it means is, well, we had the number of rows with 3 and by 2. You want this to become a 2 by 3, where the number of columns become the number of rows, and the number of rows become the number of columns. That means that now every row will become a column. So B transpose, this is how we notate it, will now become like so. So you'll take the 6, 5, you'll put it as a column, you'll take the 3, 2, and you'll put it as a column. And how to check? Well, now you have 2 rows by 3, which is what we wanted. So you're on the right track. This is basically what transpose is. And I think the last thing he also mentioned was the identity matrices, and I think matrices, and you know what these are. So if you have a 3 by 3, that means that, well, you have something like this, where in every column you have at least one pivot, and that pivot is in the value of 1. So you have the number of pivots is the same as the number of variables, and you want it in a reduced form as well. So that is 1, 1, 1, and it's the only non-zero element in every. So now if we have a 2 by 2, that will look something like this. You have a 1 here and a 1 here, and nothing else in that column other than that pivot. Let's say 4 by 4, that will look something like 1, 2, 3, and it's reduced, yeah. So 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. Again, you have a pivot, it's reduced because the columns match the reduction thing. Okay. Then he talked about, well, I think mapping functions. If I'm not mistaken. So he talked about linear maps. Yes, he did. Okay. A linear map is basically a function that you'll give it a set of your vectors, and it will perform a linear function to it. So you can like multiply it by something, you can add it to something, as long as the linearity relationship is maintained. I think you have to know how to prove linearity of maps. That is basically that this function is actually linear. There is an addition and a multiplication proof, something that states that, well, if you basically add it, well, it will remain added. It doesn't actually change its linear behavior, and same when you go to multiplying it. It's in the slides, and I think it's quite clear. If you're not getting it, do Discord me. I think that's better than explaining it here. I think there's way more important things I should be mentioning. But basically, he also discussed what kernels are. So he talked about what kernels are, what image are, and dimensions are. I think dimensions is pretty clear. It's, well, basically the number of variables you have, so the number of dimensions you can represent a certain vector space. Kernels is basically if you have a linear function. So all of this is we're assuming you already have a linear function, so f of whatever it takes. So in other words, let me draw it out. You have a vector space L, and you basically apply the function on it, and you get now a new vector space. I'll just call it W. Kernels are basically a set of vectors, so it's a set of vectors, such that when you map them using this linear function, whatever it is, it will all map to a value of 0. So this is what we call the kernel of L. So that is all the set of vectors in L, such that when you map them, they will become 0. And an image is basically the set of vectors, such that when you map them, you're gonna get, so this is going to be the image of L, such that when you map them, you're going to get non-zero elements. And this here is actually what is the image of L. So this image is after you apply your linear mapping. A kernel is what before you apply a linear mapping, and a kernel is everything that goes to 0. Then he will ask you something like, what is the dimension of your kernel? Like, what is the dimension of your set of vectors in the kernel? This will be the number of basic solutions, aka, well, the number of non-pivots. And one way to relate them is when you were, it's not, I don't think it's actually that related, but one way of remembering, or the way I like to remember this, is because if you have the basic solutions, all the non-pivots, you actually just completely removed, well, you removed it, and then you just set it as 0 later on when you actually defined your basic solution. And so that maps to 0. But I don't think that actually is true, but this is how I like to remember it. Like, I don't think that's the reason why they said that, but I think it's a good way of remembering it. So just remember dimension of a kernel, everything that maps to 0, hence the number of basic solutions. The dimension of an image will basically be, well, the number of your variables minus your kernel dimension. That is basically everything else than your vectors that's set to 0. That actually means number of variables minus the number of your basic solutions. That's the dimension of your image. I don't know if you made the connection already or not, but this here is actually your number of pivots, because if you have a number of variables, they're either pivots or not. So it's either as a pivot or it's not a pivot. And so, well, if you subtract the variables from the non-pivots, then you're going to end up with the pivots. And personally, I think that's what was important in week 3, is that you know how to multiply, you know how to transpose, and you know how to get the dimensions of your kernel and your image. So I'm going to go to week 4, if that's okay with you. Again, this one is quite simple as well. It should be quick. So you have in your week 4, that was basically you had to, it talked about combining two functions or mappings. That means you have something like, you have a matrix. Oh, one important thing actually is this function that you use to actually map something, so x, y, z, and what it does is that it returns you a vector where x is added to y, and let's say x is also added to to z. I don't know why I'm saying v, but z. This can be represented by a matrix. So let's say A will be, and this matrix is essentially what is happening here, I would say. But yeah, so this is basically, it could be represented as a matrix, and this matrix, such that this matrix, that if you multiply it to your x, y, and z, you're gonna get this answer. And this is also one way of, well, finding out what your matrix actually is. So here you know that this is 3 by 1, and you want to end up with a 2 by a 1 by 2. Maybe this actually doesn't work, does it? I'm not sure, but I will look into that. But the basic, maybe actually it should have been then something like this. But here it doesn't matter. What matters is that you can be representing it in terms of a matrix that will help you define like that function itself. And this is what basically week 4 is sort of concentrated on. Oh boy. So I'm just gonna get rid of this bullshit because yes. Let's just select all and delete relay. Okay, basically what's going on is that if you have multiple, you want to basically combine two functions or mappings. So you want a matrix of such a combination, let's say, where G is a matrix. So you have G as a matrix that represented a function, and F is also a matrix that represented a function, or F is just a function, or G is just a function. What this means is that you want to apply the function GF on a set of your like just a vector. And what this means is that you first want to, you always go like, what is this? Left to right, so in this direction. You always apply whatever is closest first, and then you keep expanding on. So that means you first want to apply the function f, and whatever the answer of that, you want to apply it on the function g. So it's important that you know the order of applying your functions, because I don't think this will actually give you the same answer as if you first applied it. Well, it will definitely not give you the same answer if you would have applied g first and then f. So these two are not actually the same. So always remember whatever is closest to the vector first, and then just keep going further. I think it would be nice to give you an example for this, because I saw some people getting confused, or at least it's where most of the calculation mistakes really happen. So let's just assume you have, let's say you have f of x1, x2, and x3. If you give it 3 variables, it will give you x1 minus x2 comma x2 plus x3. And let's say you have g of y1 comma y2 will be 2y1 minus 2y2 comma 3y2. Then g of f will be first apply f of x 1, 2, 3, whatever answer you will do in g. This one will give you this result. So now you're basically saying you want g of x1 minus x2 comma x2 plus x3, which means you can treat this whole thing as your y1 and treat this whole thing as your y2, because this is what g takes as parameters. So now what this means is this is going to be now your 2, and y1 is x1 minus x2 minus 2 times your y2, which is x2 plus x3, comma, don't forget that, a lot of people forget that, 3, and then your y2 is your x2 plus x3. And just solve it, simplify it, and you're good to go. Okay, let's see, what else? Then he also talked about the inverse. The inverse is quite easy. If you want to find the inverse of something, well, if you have a 2 by 2 matrix, it's really easy. The inverse of a matrix will be 1 AD minus BC times DB minus BC.
How would this exercise appear as a question in the exam? Like, what can we ask them so they have to do this?
Okay, sorry, I was listening to Lilia's question. So somebody asked, what kind of questions would you get when you're having the combining two functions or mappings? Well, I guess it would be something like, oh, you have this function and you have that function. What is going to be the m of whatever function, and then with whatever function, really. Like, I think it will be very direct where you'll actually see this notation as well. But just to be sure, I'm checking right now the assignment of week 4. And it says, so the way he said it was construct the composite function gf of x1, x2, and x3, and derive this function from the matrix M of gf. So you basically want to find this. He gave you g, and he gave you the function f, and he gave you, you basically want to come up with pretty much this. I think I really cannot imagine what other way he would be asking this other than that. But once you see this weird notation, just know this is what he's talking about, and the way he addresses it is composite functions, I think, most of the time. So you compose functions together, pretty much. I hope that answers your question. But let's go back to the inverse for now. So now you have an inverse. If it's a 2 by 2, you'll get let's say you have an A, B, C, D, then what you need to do, the inverse of A will be 1 over AD minus BC. And what you do is just swap these, so that's DA, and just negate these. So that's minus B minus C. And voila, you've got your inverse. This you should learn by heart. My amazing drawing skills. Only if it's 2 by 2, this would work. Otherwise, if it's any other value, what you need to do is, well, take that matrix. So let's say you have 1, 2, 3, 2, 5, 4, 1, minus 1, 10, whatever really. What you want to do is you do your bar, and you basically want it to go as an identity matrix. That is because you have A times your A minus 1 is the identity matrix. And basically what you're doing is you're really trying to find this A minus 1. And this is one way to do it. You're going to start reducing this part such that it looks like this part. And, well, I would love to solve this with you, but I think it's going to take some time. So I'd rather not, because there is the one with basis transformation. I think that's more tricky. But if you're up for staying longer, I could do that. But basically what you'll end up with is something that looks like this. And you get a 54 minus 23 minus 7. And this is actually the correct answer. But what you see is that once you try to reduce this form into this form, you'll start getting numbers here. And this actually is your A minus 1. Practice and it will make sense, really. But let's go to, that was pretty much week 4. That's all what he talked about. Week 5 is the quite tricky one. I would rather do that with you. So everybody's nightmare, including mine, is week 5, where he talked about basis transformation, and he also talked about determinants. I will start with this one because this is the really tricky one. Basically, remember when I told you when you find your basic solutions, so what are bases actually? The basis is basically, a basis vector is basically your independent vectors in a span. So a span is like when you had like R and then the dimension of the span. So every vector will have a dimension of 3 in it. And anything that's all the independent vectors in a span, yeah, those can be independent. So one way to check, there was, I think, a question, if you have a span, how do you know that those vectors are independent or not, or whether they form a span? Well, vectors form a span if they're independent. And how to check if they're independent was to reduce them to echelon form, and again check how many pivots do you have. If it's less than the number of your elements or your variables, then you know that this is not independent, it's dependent. Otherwise, it's independent, if you can actually find a unique solution to it. But basically, bases are independent vectors in a span such that any other vector in that span can be expressed in terms of those independent vectors, so those bases. So basically, again, you have a lot of vector spans, a span with many vectors, but you want to find this, let's say for this sake, 2 bases, so 2 independent vectors of each other, that is, such that any combination of those 2 vectors will give you every other vector in the span. This is the meaning of basis vector. And basically what's actually going on is if you have a linear transformation, what you're doing is that you're going from one vector space to another vector space. I already sort of showed that, but didn't specifically like mention it. But if you have any vectors here, you can go to this vector space using a certain function, a linear map. But then there's this whole thing about these vectors can be represented in terms of a basis vector, right? So you have an independent vectors, and those will be basically representative of this entire vector space because any other vector can be formed from those basis vectors. And this now leads to like this whole thing about transforming bases. And that means that if I want to perform a specific linear map, but this linear map is with respect to, let's say, basis 1, what if this vector space is actually represented by another basis, like say basis 2? So what you need to do for this linear map to actually do what it was supposed to do, you need to convert this basis 2 to be basis 1. So in terms of basis 1. Because now if you transform this basis 2 to basis 1, those vectors, well, now this entire vector space is represented in terms of basis 1. And then you can do your mapping function in terms of basis 1, which can give you vectors in terms of a specific basis. It could be the same basis, could be different basis. It actually is the same basis, at least most of the time. I will not get into that, but it will give you the same basis, like in terms of those bases. And it really depends on what output you want to get. You can either convert it back or you're satisfied with respect to the basis that you got. And this is the whole story behind basis transformation. Basically, the way they notate it is the following. If you have t in terms, you want to move it, so whatever mapping function you're having, whatever vector space, whatever this t represents, you want to do those bases from B to C. That means you want to transform the vectors with respect to basis B to become vectors with respect to basis C. And there is an equation for that. The proof is on the slides, that if this is the case, it's basically C minus, well, inverse of C times, make this capital better, times B. This is transforming bases, only the bases. They also found out that if you have C to B, that is actually just the inverse of this entire transformation. But this also could be B minus 1C. Like those things are the same. But then it's like, well, if you already computed this, just compute the inverse, you'll get the other transformation, like the transformation back. Yeah, and this makes sense because if you go in one direction, the inverse will be in the other direction. So if you go from B to C, the inverse will go, well, to go from B to C again will be the inverse of what you originally did. So this is what you really need to know. And now what they also discuss is, okay, what if I have the mapping function that I want to actually transform? So let's say I have AB, I have the linear function AB, but now I want it to be able to handle bases in C. Well, if that's the case, this is the equation. And the reason behind this, the long story short, is that, okay, your AB can handle vectors represented in the basis B. So first thing you want to do is you want to take those bases that are represented in C, so your original basis, you want to transform it to B such that AB can handle it. And then after that, transform those bases again to C, such that now you get whatever the transform in AC will be. So again, if you want to find AC, if you have AB, then first you want to change C to B so that AB can, well, sort of the way I like to think of it is work on it, like be able to handle this. And if that's the case, then go from B to C again. That's one way of remembering this equation. And that is also why in Suezo, when you had the weird linear map from 3D to 2D, you said something like B inverse 2 times your matrix times your B from. That is because here you're actually dealing with bases that you want to go from, and here you're dealing with bases that you actually want to go to. That is something a lot of students also found confusing. But this I think is enough to help you with solving the questions. This really is all what you need to know. One thing to keep in mind is if you have matrix A times B times C, this could be A times BC, so like this, and it's also the same as A times B times C. Those two are both correct. If you have AB, it is definitely not the same as BA. Some people also ask me, why is this the case? Well, here you're only changing what you're multiplying with what, but the order of multiplication, you're still going in this direction. So you're still multiplying from left to right. You're still multiplying A by whatever value you get here, and whatever value you get here, you're multiplying B by whatever value you get in C. So you're still keeping the property of going from left to right, and here as well. But in this case, what you once went from left to right, now you're switching them again, and now you're going from, well, B times A, and, well, I know it's confusing, but that doesn't actually work out. But this is true. So it's, yeah, so this is true. Just keep that in mind. And I really think this is enough for week 5 for you to know in terms of basis transformation, that is. We still have the determinant to go to. But if you have, I would recommend going through the assignment for week 5 of 2019. This is actually way simpler than what you had in Suezo. But yeah, it's still, I think if you try to apply this on the questions of Suezo, you should be getting the same answer as well, because I also did that. But I would understand why people thought it was confusing, that you went from this to this. But initially, this is what you were trying to do. You were trying to change the basis into an appropriate format for the linear matrix, well, the mapping matrix, sorry. And here you transform the basis again. Also, one thing to be clear about is this is a mapping matrix. This is the matrix I was telling you about that actually represents a function. So this function is a linear map. It maps your set of vectors into another set of vectors. And this mapping matrix does the same thing, except it's now represented in a matrix instead of just a function. Yeah. And here you're transforming basis. And what you get here is not the final answer of your transformation, of your mapping, that is. This is just a new mapping matrix, but now represented, well, with respect to basis C. This is also a lot of things students found confusing, is that they think you get the final answer of your mapping, but this is not true. You just get another mapping matrix that you can now apply to your set of vectors that are represented with the basis C. I hope this is a bit more clear. I will assume so until Lilia basically tells me the questions you're having. And I would say let's go to the determinants now. It's quite simple. It's just things you will need to know more than understand if you want to at this, like, I think it's a bit too late now to actually try to understand stuff. So what I did in my year, was to basically get as much as I can and just use it in the exam, and then later on understand actually what was underlying behind it. And it all makes sense after the exam, trust me. But then the determinant now, a determinant, if you have an A, B, C, D, so again a 2 by 2, the determinant is basically A times D minus B times C. So this is like your base case. Now if you happen to have more elements, so let's say you have 1, 2, minus 1, 5, 3, 4, minus 2, 0, 1. How can you do this? Well, basically, you will concentrate on the first column. So keep that. And what you want to do, you want to take every element in that column. So you're going to start with the 1. And then you're going to exclude anything that is in the same row or the same column. So you're going to exclude pretty much this entire first row. And you're going to take the determinant, so the determinant of the rest. So in this case, you'll get 1 times the determinant of 3, 4, 0, 1. And you will have something called alternating signs. Why that is the case, there's a proof, but you don't need to know that for the exam. You'll have a plus here and a minus here. And then you take the next element, so that's the 5. And now, again, exclude anything in the same row. So you're going to take the determinant of pretty much these. So you're going to take the determinant of 2, minus 1, 0, and 1. And then alternate the sign. So you always start with a plus. And now you're going to go minus, so plus again. And this is, no, yeah, there you go. Plus again. And now you take the third one. And you basically want to exclude this row, so you'll take the determinant of these two. So that will be minus 2, and then 2, minus 1, 3, 4. And now this will be 1 times, and you use now you have a 2 by 2, so you can use this. And that will be, so that will be 3 minus 0, minus 5 times, in this case, the 2, well, minus 0, and then you get a minus 2 here, and this will be 2 times 4 is 8, minus 3 is plus 3, this could have also actually here a plus, and whatever your value gets here is the determinant of this. So one thing you need to know is if you're describing a determinant, don't put round brackets here. This is wrong, because now you're actually representing these numbers as a matrix, and this is wrong. A determinant is basically single bars, and what this says is that it doesn't say that this is represented as a matrix or anything. This says that these set of numbers are later going to become one final number, just one number, so that a set of operations are going to be happening here, and this will result into one number. So it's very important that you distinguish those straight bars from the round brackets, because then the entire meaning changes, and Luke is quite strict about this. What is a determinant? Basically, the determinant is an area under 2 vectors, or n vectors, really. So in this case, it's the area under 2 vectors, and in this case, it's under, well, I think 3 vectors. There is another way to actually do this, because as you notice, it's sort of like a recursive process. So now if I had one more row, or one more column. Oh, so one important thing is that I think also the determinants are always n by n. Same with the inverse. They're always n by n. You'll never have more rows than columns, and vice versa. You'll always have the same number of rows and the same number of columns. And now if I were to add another one, it would have been even worse, because then you'll pick the first column, and then in that first column you're going to get a determinant of like a 3 by 3, so you'll have to repeat that procedure again, and it's just hectic and such a waste of just effort, really. So another way to do it would be to basically if you have a 3 by 3, it's still fine, but once you get more than that, just reduce it to echelon form. Actually, not reduce, just basically convert it to echelon form or transform it to echelon form. So that means that you should do not have your pivots specifically to 1. So you don't want it reduced, because then you're going to actually lose the information represented in this matrix. What you want to do is just keep it in echelon form, and then you're going to multiply the diagonal with each other. So let's say I will just come up with an example really, because yeah, I'll say you have 1 0 0 4. Let's say this is after you already put it in echelon form. So you have 0 here, 3, a 2, 1, and a 0 0 5 2, and let's say here 0 0 0 minus 1. Then this is already in echelon form. So what you're going to do is you're going to multiply the diagonal. And that will be, in this case, the determinant of this will be 1 times 3 times 5 times minus 1. However, it's important that you actually keep track of how you transform this into echelon form. That is because every time you swap, if you swap a row, so if you swap Ri with row j, row I with row j, then the determinant you get is basically going to be the negated determinant before that swap row happened. This is really important. So let's assume during the echelon form you actually had to swap row 3 with row 4. That means that now what you actually had as a determinant of minus 20 becomes 20 because of that row swap. I'm actually, after time, I'm not sure if you would be interested in seeing examples, but the 3 rules that you need to keep in mind is basically, again, if you swap a row, then you need to negate the determinant that you get. And if you multiply an entire row by a certain value, then you also need to multiply that value by the determinant. And if you add 2 rows, it's fine. You don't need to do anything really, so just ignore even that. But what's important is if you swap and if you multiply an entire row. And the swapping, if you happen to swap the first row with the 4th row, this is not, again, not considered 3 swaps. This is not considered 1, 2, 3. This is wrong. It's just 1 swap. We don't actually count how many layers in between there was. So again, if you swapping row 1 with row 4, this is just 1 swap. Also, don't confuse it when you're doing transformations. So if you have something like row 1 is 2 times row 2, this is not the kind of multiplication we're talking about. What we're talking about is if you have row 1 is now a new constant multiplied by the entire row 1. So you take an entire row like this one and you multiply it by 10, let's say. Then this case is what we're talking about, and not if you were actually just doing a normal addition here. So actually, if this constant you were multiplying by the row you're actually changing, then you will have to also include it in the determinant. So just pay attention. If the result of the row have been multiplied previously by a constant, then just keep track of that constant so you can later on multiply it by your determinant that you found. And that was basically week 5, really. I really hope the basis transformation makes a bit more sense, or at least gives you a bit more confidence on how to tackle the exam questions. But basically, yeah, then we'll come to week 6. Okay, let's see. Week 6. It talked about, we're almost there. It talked about characteristic polynomials. It talked about eigenvalues and eigenvectors. I will just give you right away how to get those and not actually go into depth on why this is the case. But basically, what all you will need in this is if you have a matrix multiplied by a vector, so this is again a mapping matrix, this will give you at the end just the same vector, but then there are some there are such mapping functions such that if you multiply it by a vector, it basically outputs just this constant multiplied by the same vector here. So this vector is the same as this vector. And this constant, we would call it the eigenvalue, because it's a special case where, again, it's just basically the mapping happened to be just a scalar times your original vector. And those make our lives really easy. And, well, one way to find those is through characteristic polynomials. And what this means is that basically if I want to find now this eigenvalue here, you basically say that a times v minus this will be 0. So basically I just moved this there. And now you're saying is basically you want, if I were to formulate this, this will be a minus lambda I times v equals 0, because this v is the same as this v, so you can take it out and just put a bracket here and just, basic simplification. And now what this is saying is that this should be equal to 0, because you know for a fact you actually have a value for your vector. So you know that the result of this should be equal to 0 to satisfy this equation. This is the whole idea behind it. And the determinant of this value is what we call characteristic polynomial. So if he asks you to find the characteristic polynomial, then you only want to find the determinant of this value here. But if he's asking you for the eigenvalues, then you need to solve that the determinant of whatever this is here is equal to 0. So you need to distinguish between those two, because if he's asking for a characteristic polynomial, then you do not actually need to go all the way to the end and solve it. But if he's asking for eigenvalues, then whatever you got as a characteristic polynomial, you're going to set it to 0, and then you're going to solve it to find your eigenvalues. I will quickly go through an example for this, because I think, yeah, I think, basically one more thing. For every eigenvalue, you can find an eigenvector. It is also something you'll need to know, and this is the eigenvector. Long story short, what is going on is that the eigenvalues represent, well, eigenvectors represent basically a direction in your data. So it doesn't actually, I'm not sure how to describe it, but basically if you had like a bunch of your data, you can have multiple eigenvalues that will actually represent the direction of how your data are shaped, in a sense. I wouldn't say really shaped is the right word, but basically one eigenvalue will show you this direction, one eigenvalue will show you this direction, and the eigenvalue will tell you how far, how much is this vector actually represented in the data. So you can see, like in this data, the distance here is quite big, so it's kind of elongated on this distance. So your eigenvalue is going to be in that direction, same direction as this line, and it will be definitely higher than the eigenvector that is eigenvalue, well, vector that is actually representing this direction or this elongation in the data. I think it will be more clear when you take data mining, but basically this is what you need to think of vectors, and what you really need to know in the exam is actually how to get them out. I think later it will become clear on why do you need them. So for now, I'm just gonna quickly walk you through an example of how to find them. So let's say you have your A is 1353. Then to find, okay, first let's find the characteristic polynomial. Characteristic polynomial. That means that you want the determinant of 1353 to be 0. That means if you have 1533 0, again the single bars to represent that we're finding the determinant here. So that was again A D minus B C. So that will be actually, sorry. Okay, a common mistake students tend to do, actually it's something I also wanted to discuss, and instead I fell in the same mistake, is that this is wrong. Because here you're actually finding the determinant of A, but for the characteristic polynomial, you want to find the determinant of A minus your eigenvalue I, which your eigenvalue is still unknown. So actually, what you will need to do now is the following. You first want to find A minus lambda I. I is representative of the identity matrix. So you're saying you want to find 1353 and minus this of 1001. So this is telling you basically the following, because if you just simply multiply this, the 0 is 0, 1 times lambda is lambda. So this will now be 1 minus lambda, 5, 3 minus 0 is 3, and then 3 minus lambda. And to find the characteristic polynomial, you want to find the determinant of 1 minus lambda, 5, 3, and 3 minus lambda, which in this case will be A times D minus B times C. So that will be 1 minus lambda times 3 minus lambda minus, and then 5 times 3. And this will be 3 minus 3, the following. And if we further, I think we can simplify this to this. And minus 15 and plus 3 is minus 12. Oh, yeah. So this here is your characteristic polynomial. And now if I want to find, I would like to keep the thing next to it. Now if I want to find the eigenvalue, then to find the eigenvalue, then you're going to set your characteristic polynomial to 0. So that means that your lambda squared minus 4 lambda minus 12 will be 0, and you want to find values for this lambda to find your eigenvalues. So that means that, well, this will be this. So your lambda is 6 and lambda is minus 2. So this is going to be your first eigenvalue, this is going to be your second eigenvalue. And now to find the eigenvectors, you're basically going to take each eigenvalue and you're going to put it back in the equation and, well, try to find So here, for example, I'm gonna go with the, well, let's go with the first eigenvalue. Okay, let's just, you can just pick, it doesn't even, just to show you, even the order doesn't matter of which eigenvalue you really take. You just take any of the eigenvalues. I'm gonna get rid of this now because we'd like to keep the other part. So now, let's say you're gonna go with the eigenvalue of -2. Then what you want to do is you basically, you want to have a times vi is the same as lambda I times vi. So if you do the matrix on a vector with the eigenvalue of -2, you want the same vector to be here. And basically what you're going to do is that your a minus, it was a minus lambda I should be, times v should be 0. So actually what really matters is this part. So now you know that a minus your, well, -2 is +2i. This is now what was once 1533 will become, well, basically 1533 plus 2002. So that will be your 1 plus 2, that's 3, 5, 3, 5. And actually what you want to do now is find a solution or this of this where this holds. So the vector of your lambda being where your eigenvalue was -2 will be, this is your, well, v1 and v2. So those are the vector elements that you're trying to find here because it's obviously of 2 dimension. So then if you reduce this to echelon form, I was just going to say R3 is R3, oh, R2, my bad, R1, that is 3500. So you know that basically v3 times v1 is, well, plus 5 times v2 is 0. So 3v1 is minus 5v2. I think I'm confusing stuff here actually. But I think I did something wrong somewhere. But basically what you need to do is take this one, so your a minus lambda I, and then you want to reduce it to find your eigenvectors. And you do that for every, well, eigenvalue. If we do have enough time, I don't know if you guys want to stay. If people want to stay, we can actually do an actual example where I can show you that this actually holds. But I really think it's better if you actually do the assignment yourself and just try it out, really. But this is all you need to know in week 6. So characteristic polynomial is when you take the determinant equal to 0. Then to find your eigenvalues, you set that characteristic polynomial to 0. And then if you want to find your eigenvectors, then you take each eigenvalue and you're going to basically, well, substitute it in your a minus lambda I, and you want to solve it such that, so the whole idea is that if you have a minus lambda I, you want to multiply it by v such that it will give you 0. So that means you're going to take the matrix you found here, so that is in our case this 3, 3, 5, 5, 5, 3, 5. You want to multiply it by, this is a 2 by 2, so you need this one to be a 2 as well. So like this will be 0. So now you have the equation of, yeah, so you want to just find this 3, 5, 3, 5, bar 0, 0, which you can just ignore everything in the bar. You solve that and find the solution of it, and this solution will be the vector, your eigenvector. Week 7 is really simple. At least all you need to do is really just memorize the stuff that he has in the lecture if you want to be able to solve it in the exam, even if you don't get what it means. But basically, I'll just tell you what you need to know. So if you have this, where v is your vector, this means you're trying to find the length of your vector v. And that will be the square root of your first value in the vector plus the square of your second value all the way up until your nth value. The distance between two vectors, or the distance between endpoints, this means that if you have, let's say, vector v, vector w, this right here is what you call dvw, which is the distance between endpoints, and that will be the length of v minus w, which means this is also the same as if you did w minus v, because you square everything anyway, so the sign will be gone. And this basically means that whatever the first value of in your v vector minus the second, well, the first value in your other vector squared up all the way until you reach your last element. Then you also have the inner product that you need to know. That is basically represented like this, and this means that you're going to multiply, well, it will be the sum of your elements multiplied. So for example, if I had 1, 2, 5 to be my v, and my w is 2, 1, 1, then the inner product between v and w will be those, so the elements in the ith will be multiplied, so that's 2 plus, and then these two multiplied, plus these two multiplied. That's the inner product. And since you do that, you can actually rewrite this into that the length of v will just be the square root of its inner product. So the inner product of itself, because this will give you basically the squared part here. You multiply each element by itself, so you'll get the square part, and then you'll need the square root to actually get the length. Yeah, so the last thing you also need to know that is important is the cosine of, well, the angle between two vectors is going to be the inner product divided by the length of the vectors. This is just something you'll need to learn by heart if you don't understand why this is the case. And if you want to understand why this is the case, I think the lecture slide proved it. And if you don't get it, you can always Discord me. But this is really what you need to know, or the basics that you need to know to basically be able to do week 7. He then introduced as well orthogonal vectors. That means that your vectors are, well, perpendicular. And if you do have actually orthogonal vectors, then you know that the inner, this is like something you need to know, that the inner product will be set to 0. And there is a proof of that. So if he asks you, okay, you have vector v, vector w, are those two orthogonal? Well, you check, okay, is the inner product equal to 0? If yes, then they are orthogonal, or, well, perpendicular. If not, then they're not. So the whole idea actually behind the orthogonality is that basically, if you have a set of vectors, you basically, if you have independent vectors, so if you have, it's important that they are independent. If you have independent vectors, let's say you have, let's say you have this vector w, and you're basically having another vector v, then if you wanted to project v onto w, the easiest way to do it is, well, shift v at the shortest distance to w. So you basically now want w here, and you want this v to be projected such that it's on the same line, like it's the shadow of basically on w. So you want this v to be now, it's sort of like if you're looking here, so this is the my beautiful eye, then you sort of want to see v projected on w, and what Luke said was the shadow. I just like to think, well, you want v to be on w because you're projecting it, easy peasy. But then how to actually do it? V was initially here. How to project it? Well, the mathematics came together and decided it's easiest if you do it on the shortest distance, and that distance is basically the perpendicular distance from v to w. And that's the whole idea behind the projection, and why orthogonality was like important, is that now if you want to find the projection, so if you want to find the projection of v onto w, so this, you're projecting v onto w, that will be the inner product between vw divided by the inner product of w itself times the vector w. So this is actually a vector. This will result in one number, a scalar number, and this whole will result in a vector. And it will tell you this is now the vector v that is actually on w. And yeah, that's pretty much it. What you get here, a big misconception is that people think what you get here is the actual value of v, but that's not true. That's not the v now on w, but it's actually the transformation, well, the distance needed, or the vector actually needed to get you from this v to this v prime. So it's basically, that's why in Gramsci the Gramsci, whatever he does, he was basically, what he was trying to do is that he's saying if you have a set of independent vectors, so let's say here you have a set of vectors and they are independent, his procedure was to find, basically make each vector orthogonal to the other. So all of them are going to be orthogonal to each other. Meaning, let's say you had vector 1 and vector 2, he would first place vector 1, and then he will try to find a new set of vectors, vectors 2, such that it becomes orthogonal to v1. And now if you add another vector 3, he will take this vector 3 such that it's orthogonal to both v1 and v2. So this is a 90, a 90, and a 90. This is like, and assume it's in a 3D dimension. And so on. Now if he wants to add a new vector, vector 4, he wanted placed such a way that it's orthogonal to both vector 1, vector 2, and vector 3. This is what Gramsci is actually doing, and the way he's doing it is the following. So basically what he's doing is that if you have a set again of v1 all the way up until vn, he first places v1. So he says the new vector, well, in that set will just be the same as v1. So that is just placing v1 here. Then he will say, okay, you're going to take now v2 prime to be whatever you had minus the distance of v2 v1 prime, comma v1 v1 and v1 prime. And this one was basically the projection of v2 on v1. So basically he's trying to find the orthogonal distance, and then he's basically shifting that vector there. And then basically what now he's doing in v3 is going to be v3 minus, and then according to v1, that would be v1, 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 but then also v with respect to v2. And this keeps going on up until the number of vectors you have. And what this will give you at the end are orthogonal vectors. So vectors, the same set of vectors, but now they're orthogonal to each other. Again, this is better if you practice it. Now comes the concept of orthonormal. And basically what this means is that you want to make the vectors in terms of 1 unit size. You want to normalize it. That is because if you can have a lot of like, if you have like a grid here, you can have so many kind of vectors. Like they're so big, some are so small, and the calculations become very complicated that sometimes it's better that if you just limit all those vectors to 1 unit size. So basically 1 box in a grid. So now all the vectors are normalized such that they're scaled, so their relationship is maintained, but then their size is still not larger than this 1 unit size. And the way they do that is you take the vector and basically divide it by its length. This is how to find the orthonormal of a vector. Just take the vector, divide it by its length. There's also one property you need to know as well, is that if you have vector, like 2 vectors that are perpendicular, then the length of the vectors squared is going to be the same as this length on its own and this length as its own. This is a property that holds out of like orthogonal relationship that I think you should know in case, I'm not sure in case of what really, but I guess it's one way to check if they're also orthogonal. I'm not sure about that. But if you were to check whether 2 vectors are orthogonal, it's always better to just say that VW, the inner product of them, is equal to 0. And I think this even derives from this property anyway. But I remember on Suezo he asked something about this. So I don't remember the question, but you can check it yourself. You could use it in that case. Yeah, and I think there's also one not that important property. I never saw him asking something about it, but if he does, is that if you have the basically vector minus its perpendicular vector is the orthogonal, like the orthogonal vector. I'm not really sure when to use this, or when will he ever ask about this, but maybe he did in the assignments, I'm not sure. But this is pretty much all what you need to know for, in my opinion, week 7. If you now have any like in-depth questions, I can answer that. Or if you have any assignment questions that you did not know how to solve, we can solve that together. Other than that, I think that's all you need to know for the exam.
There's a question if you can maybe give an example of transforming bases.
Okay. So I just got I got a question of if I can give an example of transforming bases. And well, yeah, we can take an example from the assignment and we can solve it. Let's do that. Just give me a second to actually get out a question.
There's also a more general question. What are matrices in terms of vector space? If you can answer that maybe.
Okay, I also got another question right now. What are matrices with respect to vector spaces? I'll answer that quickly. I'm not really quite sure what you really mean, but if you have a vector space with multiple vectors, I guess a matrix represented in that vector space is, oh, okay, I think I understand what you mean now. So you're saying if you have a vector space in the basis of C, what does it mean that you have a matrix in terms of a basis C? Or at least I hope that's what your question is. That means that whatever linear transformation you're making, so whatever A is going to be mapping this vector space to another vector space. And what it means that it's in terms of C is that it maps vectors that are in terms of basis C. So if your vectors are represented in terms of basis C, then this is the linear map you will need to get it into this vector space. But if those vectors were in terms of basis, let's say B, then you cannot use this one. It will not actually give you this vector space because now you have different values. But you could use another matrix in terms of basis B, that same matrix that will actually take it into that vector space. And those are just related somewhat because of transforming those bases into each other, because it's a property you can do with independent sets in your, basically, yeah, this is the whole property of bases, is that they try to find a relation between bases such that you can transform them into each other, so that you also have a relation between the matrices that are used to map them into the other vector space. That's pretty much what it means, that this is what a matrix is represented in terms of a vector space. If I did not get your question correctly, please let Lilia know of that. But back to the giving an example about transforming bases. I will take the first exercise in assignment 5, 2019, because, well, I think it's quite representative. It says, okay, you have two bases in the span R2. You had the first base was U1, U2, which is basically 1, 2 and 3, 5. And you had C, your second base, which was in terms of V1 and V2, and that will be, so all of that is given. And now they're saying find the basis transformation matrix Q, and that is the transformation from C to B. So you want to transform those bases into those bases. And the way to do it is basically we know that to find this, we said that it holds that you could do B inverse of C, right? So now what is our vector, what is our basically matrix B? Our matrix B will now be of, you take this vector u1 and you put it as a column. That is because our B now is 1, 2, 3, 5. That is because what this means now is this is all representing u1 and this entire column is representing u2. And that's why you take the entire vector and put it as a column. So this is how you find your matrix B, your basis matrix B. And you want to find the inverse, so B minus 1 will be 1 over AD minus BC, so that's 5 minus 6 times, you swap A and D, so that's 5 here and 1 here, negate B, negate C. This is basically how to find the inverse of 2 by 2 that I told you need to memorize by heart. And this will give you a value of minus 5, 3, 2, minus 1, I believe, because here you only get a minus 1, so you just basically negate everything. So minus 5 plus 3 plus 2 minus 1. And then you're going to find your matrix C, because you also need that. Again, you put the vector in a column, so that's 1 minus 1, 1 minus 2. And now to find the transformation to go from C to B, it will be the inverse, so minus 5, 3, 2, minus 1 of B times your C. And this is a simple matrix multiplication. So again, for every row, you'll take every column. So in this case, I think, actually, yeah, you're going to get a 2 by 2. And I think I will just look at the answer, honestly, because unless you want me to do the multiplication as well, but I think the multiplication is quite clear, you'll get this value for CCB. And now we basically, now you want to find the transformation of from B to C. So I'm going to get rid of, well, just all of this. So now let's find the transformation from, right now we found the transformation from C to B. So now we're going to find from B to C. And that you can either now recompute compute the inverse of C times B, but what you could also do, and it's probably faster in this case, is to just find the inverse of what we already found from C to B. And what we already found was the following. So now the inverse of that will be 1 over, again, AD minus BC. I think that's minus 32 plus 33, because minus minus. And here you'll have, you swap A and D and negate B, negate C. Again, it's just finding the inverse. And now this will give you the result of, this will give you just a 1. So this is basically the same matrix here. And now the question is, we want to find, well, AC. I think they already gave also AB. Maybe I forgot to mention that. Yeah. So another thing that was given, I'll actually just delete all, because. So another thing they gave later on in the question was AB. They told you that suppose a linear function of mapping, so the mapping goes from r squared to r squared, has a matrix AB, which is 35, 88, minus 12, minus 30. And they want to find AC. And AC we said will be, you have AB, you want to go from C to B, so you can do the AB, and then you want to go from B to C, so you can get the final answer in terms of C. That's how I memorized the equation at least. We already found BC, we already found CB, and we already have AB, so all you need to do is really just multiply them, and you'll get your answer. I guess I'll also go through that. So basically we found TB to C was 411 minus 3 minus 8, and AB will be 3588 minus 12 minus 30 minus 8 minus 11, 3, 4. And yeah, you basically just want to multiply it. And it doesn't matter whether you start with this multiplication and the answer you multiply it with this one, or whether you start with this multiplication and the answer you multiply it with this one. To always be on the safe side, well, there is no safe side because I'm pretty sure that you can do both, is just go always in that direction. Just multiply these, and then the answer, use it to multiply it to this one. And here you should get the answer as far as I remember.
I don't have any other questions, by the way.
Okay, so it seems like you guys don't have any other questions. There's one other thing I could also mention. I hope it doesn't confuse you, but when it comes to transforming bases as well, there's actually two ways that this happen, and it's what explains the equation, is that one, you either first map, then transform. So you first use the AB actually on this one, and then you transform it from C to B so that it makes sense. But I like intuitively, this does not really make sense to me. But it also works, and that's why the property of having this multiplied first works. But then you can also first transform, then map, which makes more sense. In assignment week 5 of 2019, it's question number 3. You can see how this holds and why it holds, and I think it will be more clear when you actually solve this question. Other than that, I really don't have anything else to say. Again, just solve all the assignments and you're good to go. Of 2019, I would even say. You have the solutions to it, and if you have any questions, you can always approach the TAs and you can always approach me. And other than that, good luck with all your exams.